Hello class, we are back with bonding. Now we want to look at bond polarity. Covalent bonds between unlike atoms which are not the same, result in unequal sharing of electrons. In this unequal sharing of electrons, one atom pulls the bonded electrons closer to itself than the other. And most of the time, the atoms that pull the bonded electrons closer to themselves are the more electronegative elements. The result is that a polar covalent bond is formed. The end with the larger electron density gets a partially negative charge, and the end with electron deficiency gets a partial positive charge. So, for example, if fluorine bonds with hydrogen, fluorine is more electronegative. You can see that. The electronegativity of fluorine is 4, that of hydrogen is 2.1. So, fluorine in this bond, because of its high electronegativity, will pull more of this bonded electron to itself, and the result is that we have a polar covalent bond that results to a polar compound. You see, this section is positive and this section is negative. You see, you can see the electron charge. Another way of representing it is this way. You see, the arrow going this way to show that this has more electron than this. So you indicated more electrons and this less electrons. So we can show it this way too. You see, this is another. This is fluorine hydrogen. You see, negative, positive. So you can represent it this way. Those are just different ways we can represent polar covalent compounds. Electronegativity and bond polarity. Difference in electronegativity and the nature of the covalent bond that will form. So when the electronegativity is 0, this is usually between two atoms of two elements which are the same. For example, hydrogen, hydrogen. Or chlorine, chlorine. Or nitrogen, nitrogen. The electronegativity of these elements are the same. So what is formed is a pure covalent compound. Take note. But when the electronegativity is about 0.1 to 0.4, we call it a nonpolar covalent compound, although this 2 pure is nonpolar. When it's about 0.5 to 1.9, we call it a polar covalent compound or polar covalent bond. And when it is greater than 1.9, then an ionic compound results. So bond polarities. So you can see this is chlorine, chlorine, 0, pure covalent compound. This is hydrogen and chlorine is a polar covalent compound. Then sodium and chlorine is ionic, you see, greater than 1.9. So let's look at this example. Determine whether an NO bond is ionic, covalent, or polar covalent. So let's look at their electronegativity. The electronegativity for nitrogen is 3, and the electronegativity for oxygen is 3.5. Subtract the electronegativities, large one minus the small one. Let's do that. So the difference in the electronegativity is 0.5. If the difference is 2 or larger, then it's ionic. Otherwise, it is covalent. If the difference is 0.5 to 1.9, then the bond is polar covalent. So that bond is polar covalent. Otherwise, it is covalent. So the NO bond is a polar covalent bond. So we have a polar covalent bond. So let's see how we can write Lewis structures of compounds. We just studied how to write the Lewis structure of elements. Let's see how we can write the Lewis structure for compounds. So what you do first, write the skeletal structure. Make the least electronegative atom the central atom. So if you look at this group of atoms, hydrogen can never be a central atom. So we can never ever put hydrogen in the center because hydrogen can form only one bond. So between nitrogen and oxygen, electronegativity increases from left to right in the periodic table and decreases from top to bottom in the periodic table. So nitrogen should be in the center. So that's why nitrogen is in the center. Oxygen can never be in the center. So we arrange it like this. So the next thing you do, count the valence electrons. Sum the valence electrons for each atom. Add 1 electron for each negative charge. Subtract 1 electron for each positive charge. This molecule does not have a negative charge. It does not have a positive charge. But in case you have an ion that has either a positive or negative charge, that's when you do this. But in this case, it doesn't have. So we are only going to sum up the valence electrons for the 3 oxygen, 1 nitrogen, and 1 hydrogen. So nitrogen is 5, hydrogen is 1, 3 oxygen is 3 times 6, which is 18. Total is 24 valence electrons. So we have 24 valence electrons. How do we arrange it around the atoms? So attach the central atom to the surrounding atoms with pairs of electrons and subtract from the total. Don't forget, a line represents 2 electrons. So that's what we are doing next. So we attach this line. So we have 1, 2, 3, 4 lines. It means 4 times 2, we have used 8 electrons. So we subtract the 8 electrons from 24, we are going to have 16 electrons left. So what do we do next? We have to complete the octet of the outside atoms first before we can go to the central atom. So hydrogen is already completed. It cannot have more than 1 bond. So we don't bother about hydrogen, but the other elements. So let's start counting. We are left with 16 electrons. So now we put 2, this 2, this 2, this 2. This is complete. We go to this, we put 2, we put 2, we put 2. We have used 12 electrons. Then we go to this oxygen, we put 2, we put 2. It's complete. We have used the 16 electrons. But if you notice, nitrogen does not have an octet. So that's a problem. How do we make nitrogen an octet? So how do we get nitrogen to have an octet? We will use either of these oxygen. See, either of these oxygen. We are going to donate and form a double bond from either of this oxygen or this oxygen so that nitrogen can have an octet. So we have added and we've recounted. We have used up all the 16 electrons that were left. If all octets are complete, give extra electron to the central atom. So a central atom is the last. But in this case, our nitrogen does not have an octet. Elements with d orbitals can have more than 8 electrons. Period 3 and 4, 5, 6, 7, 8. If central atom does not have octet, bring in electrons from outside atom to share the following common bonding pattern if possible. So you see, that's what we are going to do here. You see, either this oxygen or this anyone, they're the same. And when that is done, you see now, each of them have an octet. We can count. So let's try and count the octet. So oxygen, this oxygen has 8 electrons. This has 8 electrons. Nitrogen has 8 electrons. This oxygen has 8 electrons. Hydrogen has 2 electrons. So each of them are stable. So we want to study formal charge. So during bonding, atoms may end up with more or less electrons than the valence electrons they brought in order to fulfill the octet. This results in the atom having a formal charge. So formal charge. How do we calculate the formal charge of an atom in a molecule? It's valence electron that it brought minus the non-bonding electron that it has minus half the bonding electron. So this is how we are going to be calculating the formal charge of each atom in a molecule to see whether it gained an electron or it lost an electron during bonding. That's all we are doing. So let's look at this molecule and calculate the formal charge of each of these atoms. Oxygen, sulfur, oxygen. So the oxygen on the left, the formal charge, it had 6 valence electrons. That's what it came up with. Then it has 4 non-bonding electrons. Then it has 4 bonding electrons divided by 2. So its formal charge is 0. Let's look at sulfur. Sulfur came with 6 electrons. And it has 2 non-bonding electrons. Then it has 6 bonding electrons, 4 here and 2 here, divided by 2, 3. So generally, the formal charge of sulfur in this molecule now is +1. Then the oxygen on the right, it came up with 6 electrons, that's its valence electron. The bonding electron the non-bonding electron is 6. Then the bonding electron is 2 divided by 2. So its formal charge is 0. So sum all the formal charges in a molecule, it is equals to 0. On an ion, the sum equals to the ion charge. So write list structure. We are still continuing writing list structure and trying to see how to find the formal charge. Assign formal charges to the atom below. Formal charge is valence electron minus non-pair of electron, or we call it non-bonding electrons, minus half the bonding electron. We have to follow the common bonding patterns. So we can calculate for the different oxygens. So that's the formal charge. This is what we calculated. Then let's say that for this. So this is 0, this is 0, This hydrogen is 0, oxygen is 0, this nitrogen is +1, this oxygen is 0, and this oxygen is -1. So the total formal charge is 0. So let's do this example. Let's try this. Let's try this oxygen. Let's calculate it. Valence electron is 6. Non-bonding electron is 4. Bonding electron minus. So it's 6 minus 4 minus 2. This is 0. So this is 0. Carbon. So after that, we clean that and do that for carbon. This is oxygen. Oh, wow. Okay. So let's do for carbon. Carbon. So this is, it came out with 4 minus 4 plus 4, 8. 1 over 2, 2, 4. This is 0. Then this oxygen, 6 minus 4 minus 1 or 4. This is also 0. So that's why all is 0. So do the same for this elements here. +1 minus 1 is 0. So this oxygen is -1 and selenium is +1. We'll look at this H3PO4. This oxygen is -1 and the phosphorus is +1. Overall is 0. For SO3 2 minus, this oxygen is -1. This oxygen is -1. This oxygen is -1 and the sulfur is +1. Overall is -2. And O2 is -1. This is -1. This one's I'm sure they are 0, 0. And this is 0. So go and try and do it to get those numbers as we have told them. Let's look at some exceptions. Exceptions to the octet rule. Expanded octets. Elements with empty d orbitals can have more than 8 electrons. Odd numbered electron species, e.g. NO, will have 1 unpaired electron and makes it a free radical, and they are very reactive. Some have incomplete octet, like group 3 elements, boron and aluminum. They can have incomplete octet. Resonance. When there is more than one Lewis structure for a molecule that differ only in the position of the electrons, they are called resonance structures. The actual molecule is a combination of the resonance forms, which we call the hybrid. Look for multiple bonds or lone pair of electrons. Let's take an example. So for example, S2, SO2, it has 2 resonance structures. It has this, you see. Let me write it, let me draw it in such a way that this is S. Or you can have this. So these are the 2 resonance structures. The double bond is on this oxygen, and in this case, the double bond is on this oxygen. we draw resonance structures. First, draw the Lewis structure that maximizes the octet. Assign formal charges. Move electron pairs from atom with formal charge towards atom with. Move the electron pair from atom with negative formal charge to atoms with positive formal charge. So you see that? If the positive formal charge atom is in the second row, only move in electron if you can move out electron pairs from a multiple bond. So if the formal charge atom is in the second row of the periodic table, only move in electrons if you can move out electron pairs from the multiple bond. If not, don't do that, because they cannot expand their octet. If positive atoms are in the third row or below, keep moving in electron pairs to reduce the formal charge even if you get expanded octet. So you see, that's it. So you see these two structures. These are resonance structures. This one you can have another one again because we have 3 oxygen atoms. You can have another. You can have a third resonance structure because we have 3 oxygen atoms. So let's look at a situation where they can be extended. You can expand the octet. So first draw first the Lewis structure that maximizes the octet. So this is the structure that maximizes the octet for this. Assign formal charges. So look at the formal charges. Move electron pair from atoms with formal charge of negative towards that with positive. So you see. Then if the formal charge positive atom is in the second row, only move in electron if you can move out electron pairs from the multiple bond. But if the formal charge atom is in the third row or below, that's third row below, keep moving in electron pairs to reduce the formal charge even if you get an expanded octet. So you see here we have moved this one electron. Then we are going to move the second electron. So you see we have an expanded octet here. What does that mean? We have 4 electrons here plus 4 electrons, 8. Then we have 2 electrons here and 2 electrons. So the total electrons here is 12. But it's okay because some of can have an expanded octet. So 2 plus 2, 4. 2 plus 2, 4 plus 4, 8. Then we have 10, then we have 12. So this is okay because we can have an expanded octet. We want to look at bond energies. So we are going to look at bond energies next. So we'll stop here. Then next that we are going to do is to look at bond energies.